Length and dot product in Rn. Vector length and distance. In section 4.1, we talked about vectors for the first time. We said that vectors were a directed line segment, or a line segment with both magnitude, which is the length, and direction. So previously, we didn't really have a measure for the length. We just used the terminal point to describe our vector. So this vector we would just describe as 4, 2 because its initial point was at 0, 0 and it went to 4, 2. We want a more precise way now to talk about the length, sometimes called the norm, and that is to find the distance. So this is a lot like the distance formula, except that we are subtracting 0, because again, if I were finding the distance from 0, 0 to 4, 2 the normal way, I would say this is 4 minus 0 quantity squared plus 2 minus 0 quantity squared. I'll just say distance. And then we would say, well, that's 4 minus 0 is 4, squared is 16, plus 2 minus 0 would be 2 squared, or 4, and we would say that's radical 20, or we might even call it 2 radical 5. So that's the normal distance formula. Now let's take a look at the length using this new formula for the length of a vector. So this tells us that the length or magnitude or norm of v, our vector, can be found by taking the first value in our ordered pair or ordered triple, etc., square it, add the second one squared, and if there were more, we would continue. Well, that gives me the square root of 16 plus 4, which is the square root of 20. So it's the same exact thing, but again, we're just finding the distance using that other point of 0, 0. So this is just an easier way to do it. We can also take a look at something called a unit vector. And a unit vector is a vector that simply has a length of 1. So you can turn any vector into a unit vector by taking the original vector and dividing it by the length of the vector. So for instance, if I have vector v, which is 2, 1, negative 3, that's this guy right here. This is vector v, and the length of that vector is radical 14. I found that by taking 2 squared plus 1 squared plus negative 3 squared to get the square root of 14. Now, to find a unit vector, all we're going to do is take that original vector and divide each value by the length. So 2 divided by radical 14, 1 divided by radical 14, negative 3 divided by radical 14. The length of that vector here in orange, we'll call that u, that is a unit vector. So let's just verify that the length of that unit vector is 1. So how do I do that? To find the length of u, I'm going to take the square root of each of these values squared. So 2 divided by radical 14 squared plus 1 divided by radical 14 squared plus negative 3 divided by radical 14 squared. So again, I'm still in the square root. 2 squared is 4, radical 14 squared is 14 because the square root and the squared cancel. Same thing, 1 squared is 1, radical 14 squared is 14, and negative 3 squared is positive 9, and radical 14 squared is 14. So that gives me the square root of 4 plus 1 plus 9, which is 14 over 14, which is the square root of 1, which is in fact 1. Quite often you'll be asked to find a unit vector in the direction of v or a unit vector in the opposite direction of v, and really all they're talking about is c being some scalar. So if c is greater than 0, then u and v would have the same direction. So if you have one that is u, and I can take it times a scalar multiple to get to v or vice versa, if c is greater than 0, they have the same direction. If it's less than 0, they have opposite directions. And then, of course, you can also find some vector in the opposite direction simply by negating it. So in this case, they're asked us to find a unit vector and a unit vector in the opposite direction of v. So let's start with finding the unit vector. The unit vector, the first thing we have to do is find the length of v, which is the square root of -4 squared plus 0 squared plus 2 squared. And -4 squared is 16, 0 squared is 0, 2 squared is 4. So this is radical 20. So I'm just going to leave it radical 20. Actually, no, I'm not. I'm going to go ahead and say, well, that's the same as radical 4 times radical 5, which is 2 radical 5. So now let's go ahead and find the unit vector. So the unit vector u would be -4 over 2 radical 5, 0 over 2 radical 5, and 2 divided by 2 radical 5. And then each of these I would just simplify. So this would turn into -2 over radical 5, and 0. And this one would turn into just 1 divided by radical 5. Now, if I wanted to, yes, I could go one step further and say this is -2 radical 5 over 5, comma 0, comma radical 5 over 5. Either of those would be correct. Now, I want to find it in the opposite direction of v. So in the opposite direction of v, I would simply negate the values. So this is +2 radical 5 divided by 5, comma 0, comma negative radical 5 over 5. Now let's talk about the distance between two vectors. So I have vector u and vector v, and the distance between those two vectors would just be that line that I've drawn in white. So this indicates the distance between those two vectors. Now, what do I know about the distance between those two vectors? Well, let's think about v and negative v. Because really what I'm doing is I'm taking u plus negative v. So if I think about u plus negative v, and then I think about, remember that parallelogram rule. That parallelogram rule said that if we are adding 2, then the result is at the end of the parallelogram, the opposite corner of the parallelogram. So this would be what I get when I take u plus negative v. So this is u plus negative v. Now, what I'm trying to find is the distance. So really, I'm trying to find the distance of this vector, which, as you'll note, is the same as the distance of this vector. So when they're asking us to find the distance, that's exactly what they're saying. That's why this makes sense, u minus v, because it's going to give us that same distance as whichever way I draw it. Let's take a look at finding the distance now, and I want to show you this in two different ways. The first way I want to show you is using the fact that u minus v, that's that parallelogram rule. Now keep in mind, not a parallelogram when we're dealing in 3 dimensions, so it's not going to look like a parallelogram over here because we're in R3 now. But what I'm saying is there's 2 ways to go about this. One way is to first find what is u minus v. So in this case, u minus v would be 1 minus 2, which is -1, 2 minus -3, which is +5, and then 3 minus 4, which is -1. And then I'm simply going to find the distance of that. So I'm going to use the norm of that difference, which says to take the square root of -1 squared plus 5 squared plus -1 squared to get the square root of 27, or 3 radical 3. Now, I am generally too lazy to do it that way, but this is the way that makes sense mathematically. But let's be realistic. Once we understand the concept, we want to do things as simple as possible. So typically what I do is I skip this step, and then I just go straight to 1 minus 2, which is negative 1 squared, and 2 minus negative 3, which is positive 5 squared, and then 3 minus 4, which is negative 1 squared, and we can see that's the exact same solution of 3 radical 3. If you would, press pause and try the second question on your own. This one's much easier to visualize because we're dealing in R2. So again, it's up to you if you went ahead to find u minus v first. I typically don't do that. So I'm going to go straight to just subtracting. 0 minus negative 3 is positive 3 squared. 4 minus 4 is 0 squared. That gives me the square root of 9, which is 3. Again, you would get that either way that you do it. And so what we're saying, and we can verify this by looking at our picture, is if we have 0, 4, so this is u, and we have negative 3, 4, which is v, the distance, which I've drawn in blue, this distance is 3. Now that's the same as if I did the parallelogram rule, which would be looking something like this. Again, it's the same distance of 3. So that's the value that we're looking for. The dot product and angle between vectors. We're now going to look at the dot product, and the dot product is a special kind of inner product. So we will be learning about different inner products in a little bit, but here we're going to focus specifically on the dot product and how it's useful for us. So the dot product of u and v, sometimes called the Euclidean inner product, is a scalar quantity. So when you get to the end, you're going to have a scalar, which is just one value. And the dot product is found by essentially multiplying the first value with the first value, the second with the second, the third with the third, and so forth, and then finding the sum of those values. So for instance, if I wanted to find the dot product for u dot v for this u value and this v value, what we're saying is we're going to take u dot v is 1 times 3 plus 4 times 0 plus negative 2 times 1. So 1 times 3 is 3, 4 times 0 is 0, negative 2 times 1 is negative 2, so I get a value of 1. Now, that's one way to think about it. The other way to think about it is that I can also multiply u transpose v. So I can think about 1, 4, negative 2, multiplied by 3, 0, 1, and again I'm going to get the same value. 1 times 3 is 3, 4 times 0 is 0, 2 times negative 1 is negative 2, add them together and I get 1. So now let's take a look at some things that hopefully will jump right out at you as of course they're true, but let's just make sure that these concepts are cemented in your head. So I want you to note that if I take u dot u, so u as a dot product with itself, using my definition right up here, that would tell me that I'm going to take u1 times u1 plus u2 times u2 and so forth. But u1 times u1 is u1 squared, and u2 times u2 is u2 squared, and so forth, which really is the norm or length of u squared. So remember, this formula says take u1 squared plus u2 squared and so forth, and then at the end I'm going to take the square root. So if I square that, it's just going to negate the square root and cancel it out. So let's just look at an example. So this would be more like a proof. What I had written in blue there, this would be more like a proof because we're using things that we know. Now in an actual proof, I would say by definition of dot product. And then I would say, and this is basically algebra. And then I would say this is definition norm, and so forth. So that's more of a proof, but let's go ahead and just verify it for this u vector of 1, 4, negative 2. So if I take u dot u, it says to take 1 times 1, which is 1 squared, and then add 4 times 4, or 4 squared, and then add negative 2 times negative 2, or negative 2 squared. Well, that gives me 1 plus 16 plus 4, or 21. Now, if I did the same for the norm of u, that says take the square root of the first value squared, so 1 squared is 1, the second value squared, 16, the third value squared, negative 2 squared is 4. That gives me radical 21, but remember they want me to square that. So if I square radical 21, I get 21. Let's take a look at the properties of the dot product. Now, most of these are pretty straightforward. We've got u, v, w that are vectors, and c is a scalar. The first property says you can take the dot product in either order, so that's commutative property. The second property says u dot v plus w is the same as u dot v plus u dot w. Well, that's the distributive property. The third property is multiplying by a scalar. So the thing to understand here is because this is multiplication, remember if I gave you 2 times 3 times 4, you wouldn't multiply, you wouldn't distribute the 2. You would take 2 times the quantity of 3 times 4, or 2 times 3 and then times 4. And so that's all this next one is saying, is you get c once. The next one, v dot v, is the same as the norm of v squared. We already talked about that one. And the last one says v dot v is greater than or equal to 0. And if v is equal to 0, then v dot v must be 0. Let's take a look at some practice questions that we can do using those properties to make it a little bit easier. So the first one is u dot v. Well, this one I have to find myself. I have to do the math. So that's 2 times 5 plus negative 2 times 8. Again, that's just first value times first value plus second value times second value. That gives me 10 plus negative 16, which is negative 6. The second says u dot v times w, but good news is I already know that u dot v from this question is negative 6. So I'm going to use negative 6 times w, which is negative 4, 3. And so this one is not going to be a scalar. This is going to be a vector, and that's going to be positive 24, negative 18. And then we have u dot 2v. Well, we already know that u dot 2v is the same as 2 u dot v. So that's 2 times negative 6, which is negative 12. So again, I didn't have to do a lot of work because I'm using that negative 6 I already found. W, the norm of w squared is the same as taking w times w. So again, that's negative 4 times negative 4, or negative 4 squared, plus 3 times 3, or 3 squared, gives me 16 plus 9, or 25. And again, not the square root on that one. And then finally, I have u dot v minus 2w. So that's the same as u dot v minus u dot 2w. Well, u dot v is already negative 6. So now I'm just going to find u dot 2w. So let's go ahead and write 2w. 2w is negative 8, 6. So 2 times negative 8 is negative 16. And negative 2 times 6 is negative 12. So that's negative 6 minus this together is negative 28, so this is plus 28. So my final solution is positive 22. Let's take a look at the Cauchy-Schwarz inequality. This says if u, v, w are vectors in Rn, then the dot product of uv, and this is the absolute value of the dot product, so it's easy to get confused because there's a lot of straight lines going on, but we're saying take the positive distance, the positive dot product, that has to be less than or equal to the norm of u times the norm of v, or length of u times length of v. So we're just going to verify it here, and then in a moment it will make sense why this is an important inequality to understand. So we're just going to verify for these two. So u dot v, so this is absolute value of 2 times 1 plus 3 times 0 plus negative 2 times 1 has to be less than or equal to the norm of u, so that's the square root of 2 squared plus 3 squared plus negative 2 squared times the norm of v, which would be 1 squared plus 0 squared plus 1 squared. Oops. So let's verify. This is 2 plus 0 plus negative 2 has to be less than or equal to radical 17 times radical 2. Well, 2 plus 0 plus negative 2 is 0. The absolute value is 0. And 0 is less than the product of radical 17 and radical 2, which is radical 34. And so this, in fact, is verified. There are a few other interesting theorems that can be proven using the Cauchy-Schwarz inequality. Those proofs are in your text, so I'm not going to spend time on them other than to just give them to you as here's the triangle inequality and the Pythagorean theorem. Obviously, the Pythagorean theorem you are used to, and if you've studied any kind of geometry, you've probably seen the triangle inequality as well, but those can both be proven using the Cauchy-Schwarz inequality. So everything that we've looked at then brings us to this point of the law of cosines. The law of cosines, you may or may not remember from previous math courses, is one of two laws, law of sines, law of cosines, that we had to use if we had a non-right triangle and we're missing sides or angles of those triangles. So whenever we were trying to solve a triangle to find all the missing measures, if it's not a right triangle, it becomes very difficult. A right triangle, we have the Pythagorean theorem for sides, we have trig functions for angles, but non-right triangles, we need law of sines or cosines. So specifically, the law of cosines says that if I'm trying to find the missing measure of a side, then I can find the sum of the squares of the other two sides, kind of like the Pythagorean theorem, but I then have to subtract 2ab cosine of c, and c, of course, is that angle across from side c. So notice down here I'm calling it theta. So that's what the law of cosine says, and it's a proven law. You don't have to do any proof on it. It's true. So now, what if I did the exact same thing with vectors? So notice now, instead of angle c, I'm just calling it theta. Across from theta, instead of c, I've got the difference between v and u, which makes sense. We've already talked about the distance between two vectors is the norm of the difference of the vectors. And I'm replacing a with the norm of u and b with the norm of v. And notice I get something that looks very similar to the law of cosines, but now with vectors. So all of that's well and good, but what happens is there's some math magic that occurs, and math magic is my special way of saying there's a ton of math that went from getting to here, and some of you won't care, and if you don't care, skip the next slide, because on the next slide I'm going to go through the math. If you do care, stick with me. But the important thing for everybody to remember, whether you care where this came from or not, is the Cauchy-Schwarz inequality verifies or makes sure that this value on the top is smaller than this value on the bottom. bigger. That's what the Cauchy-Schwarz inequality says. Now, why is that important? Because to solve for cosine of theta, I need this guy, this ratio, to be less than or equal to 1. And so this is smaller or equal to, bigger or equal to. And so that's why this is going to work. So if you're into being a dork and wondering how this became this, stick with me. We're going to do that right now. All right, let's take a look at how the sausage was made. Here was my law of cosines. First thing I did was just keep this value and move these two to the opposite side. It's because I wanted cosine, I want cosine to be on the left. Okay. Now from here, I said, what is this value? Well, v minus u, as we know, is u dot u minus u dot v, because essentially what I did was say this is v minus u, v minus u. So v dot v, v dot u, negative u dot v, positive u dot u. So that's what I have here. Well, that gives me u squared and v squared here, which can cancel out with the negatives, which essentially gives me negative 2 u v cosine theta is equal to negative 2 u dot v. And then I divided each side by negative 2 norm of u norm of v, reduced those 2's, and this is the ratio that we're going to be using to determine theta. Okay, so welcome back. If you didn't join us in Dorkville, we are back now to talk about how we use cosine of theta and then the formula to find cosine of theta to actually find the angle. So I've given us an example here, 0, 1, 0, 1 and 3, 3, 3, 3. So what I need to do is, remember, I'm finding that cosine of theta is equal to something. So I have to find that something first. So I had to do u dot v. So 0 times 3 plus 1 times 3 plus 0 times 3 plus 1 times 3, which turns into 6. And then in the denominator, I have the square root of 0 squared plus 1 squared plus 0 squared plus 1 squared, and then times 3 squared plus 3 squared plus 3 squared plus 3 squared. So the first value turns into 2, the second value into radical 36. So in the numerator, I have 3 plus 3, which is 6. In the denominator, I have the square root of 36, which is 6, and then radical 2. That gave me 1 divided by radical 2, or radical 2 divided by radical 2. Now, have I found theta? No, I have not. I have found that the cosine of theta is equal to radical 2 over 2. So now let's talk about how we find theta. Hopefully you have taken calculus, otherwise you are not going to understand quite a bit of what we do in this course. That is why calculus is a prerequisite for linear algebra. So we know that cosine of theta is radical 2 over 2. This is called a unit circle. Now the unit circle is fantastic if we're able to find an exact value for theta. So for instance, in the unit circle, these ordered pairs represent cosine of theta, comma, sine of theta. So for us, because we're dealing with cosine, we're only focusing on those x values. And if you'll notice, the x value of radical 2 over 2 occurs right here. And what that tells me is that if I took cosine of pi divided by 4, I would get radical 2 over 2. So that means theta is pi over 4. Now, is that always going to work? No, because you're not always going to get a nice number like this. I might get like radical 6 or something like that. And if you get something that's not exact, that's when you're going to use the inverse function on your calculator, inverse cosine, and then you're going to put in whatever value you get, and they're going to give you then a value in radians. So make sure that you are in radians, and this is the value in radians And if you took pi and divided it by 4, this is the number that you would get. When you're finding theta, it's important to understand what kind of angle you'll be dealing with. Now, you could understand this based on the unit circle that we just looked at, or we're just going to go through it together. So if we have two vectors that are going in the same direction, so they're stacked on top of each other, theta is going to be equal to 0. So obviously there's no angle between those two vectors. If that theta value is between 0 and pi over 2 is this guy. So if it's between 0 and pi over 2, or an acute angle, then you're going to have theta between 0 and pi over 2, and so you can see what that angle might look like. If theta is pi over 2, then you've got a right angle, which is an orthogonal angle, and that word, you'll probably get sick of me saying it, but we're going to do a lot with orthogonal angles and projections and so forth. If you have an obtuse angle, then theta is between pi over 2 and pi. And if theta is equal to pi, then we've got two vectors in opposite directions because that angle would be pi. Orthogonal vectors. Before we end, let's talk about orthogonal vectors. So orthogonal vectors are vectors that are perpendicular. They're at a 90-degree angle. Now, your textbook just says, if you want to know if vectors are orthogonal, find their dot product. If it's equal to 0, they are. But I'm generally not convinced or satisfied by an explanation that just says, just do it. I like to understand why or make it make sense to me. So again, if you are in that camp, stick with me. We're going to talk about this. If you're satisfied, you believe the mathematicians that said this is true, you can move on. But again, using u dot v for 7, 7, and 2, negative 2, I can, in fact, see that 14 plus negative 14 is equal to 0. So if you're satisfied with that, that's fine. But I like to understand. And so I said, what if I put in a negative v? Well, in a negative v, assuming that it's true that these are orthogonal, meaning this is a 90 degree and this is a 90 degree, then this would be a side angle side situation, and these two triangles would be congruent. And if those two triangles are congruent, then this distance would equal this distance. So a little bit of geometry thrown in there. So let's take a look at if that in fact is true. That means the distance from u to negative v has to be equal to the distance from u to v. So on the left-hand side, I just started working through it. U minus negative v, and then the norm squared. That's how we determine distance. So really that's u minus negative is u plus v. So I've got u plus v squared, and I squared it. So I used the distributive property to say u times that sum, and then v times that sum, and then I distribute it again. So I'm just using those properties. And that gave me the norm of u squared, the norm of v squared, and then I've got two of these guys that are the same. So simplifying, I get norm of u squared plus norm of v squared plus 2 of the dot product of u dot v. Now, if I do the exact same thing on the opposite side, you can see I get to a very similar point, but that u squared, the norm of u squared and the norm of v squared cancels, and I'm left with 2 u dot v is equal to negative 2 u dot v. Now, the only way that that can happen is if this guy is equal to 0. Let's finish up with two practice questions. The first is in R4, and we're asked to determine if these two vectors are orthogonal. So difficult to visualize this, but if I can find u dot v, so 3 times 1, that's those first values, plus negative 2 times 1, that's the second, plus negative 1 times 1, that's the third values, plus 4 times 0. If that is equal to 0, 3 plus negative 2 plus negative 1 plus 0. If I add those together, I get 0. Because the dot product, sorry that u looks a little wonky. Because the dot product is equal to 0, yes, these are orthogonal. Now the next one's not quite as straightforward. This one's saying find all that are orthogonal to 4, 2. So 1, 2, 3, 4, 1, 2. Here's vector u. We're saying let's find all of them that are orthogonal to 4, 2. Now, we could draw a picture. So before I do any math, let's draw a picture. I know that this has a slope of up 2 over 4, or up 1 over 2, which means if my slope of the original line is 1/2, then the slope of the negative reciprocal slope is the perpendicular slope. So we're just going all the way back to college algebra now. So my new slope would have to be -2. So if I wanted to draw something, it would be -2 over 1. So down 2 to the right 1. And again, starting from a point that I know is on there. Down 2 to the right 1, up 2 to the left 1, up 2 more to the left 1. It would really be anything along this line would be orthogonal. But I didn't do the math. I'm just reasoning through to see what this would look like. So now let's do the math. For u dot v to be orthogonal, u dot v, which is u1 v1 plus u2 v2, has to be equal to 0. Well, u1 is 4 and u2 is 2. So that tells me that 4v1 has to be equal to -2v2. Dividing by 4, v1 has to be -1/2 v2. So really I can draw this, or I can write this like a parametric equation. I can say any of those vectors, v, would have to be some value, we'll call it t, and then v1 is -1/2 and v2 is +1. So let's test that out. Let's let t equal 2. If t was 2, then v would be 2 times -1/2 times 1, which would be -1, 2. So -1, 2 is in fact a point on our line. So we've done this correctly. So this is how I would write that. Up next, we're on to section 5.2, inner product spaces.